Methane sources and sinks, we can write a simple equation like this, where it's the concentration in the atmosphere, let's say, which changes in time based on the production term P and the scrubbing term, or the term that sinks out the methane into other forms, carbon monoxide, carbon dioxide, or whatever, at some rate. And if we reach equilibrium, then basically the loss of methane would be equal to the production divided by this rate at which the concentration is decaying. It's a simple kind of solution, and one can look at the recent changes in atmospheric methane estimates in parts per billion, and it's not really completely explained. Unlike CO2, which is a well-mixed gas, you can measure it mauna loa and get the estimate for the whole hemisphere, measure it in the at the southern pole, and a couple of sites in each hemisphere will give you a good sense of the global distribution, whereas methane is much more it reacts much more, and it has a shorter lifetime, and it has sources and sinks that are much less tractable, let's say, or they are well, they are much more local, like landfills and wetlands and so on. Okay, so it flattened out here, and then it is not completely explained why that happened, and then it has taken off in recent times, which is also not very well explained. There are many ideas suggested, but it is not as easy as looking at the isotopic signatures of CO2 and trying to back out the sources and sinks and so on, as we did for the Ice Age and various other timescales of CO2, including the delta C13 in the atmosphere since Industrial Revolution, to say that the increase in CO2 in the atmosphere is coming from burning fossil fuels and so on. Methanogenesis chemistry gives us some ideas about where it's being produced. Typically, of course, the aerobic respiration gives us CH2O plus O2, so carbohydrates and sugars can be burned into carbon dioxide and water, which is mostly what we do, and other species which rely on having the enzymes to break down these things do. This can be decomposed further into two electrochemical half reactions, in which transfer of electrons is revealed, which is always the key part of any reactions. So CH2O plus H2O gives us CO2. So remember, this is a reduced form of carbon. So when you do that, you're going to release these electrons and H plus, so you are going to get CO2 plus 4H plus plus 4E minus. So this is the oxidation reaction of the carbohydrate, and we are going to get oxygen reduction reaction, which is the other half of this reaction. So O2 plus 4H plus 4E minus is going to give us 2H2O. So you can add that up and get a net reaction out of that. Sorry, I jumped there. So yes, bacteria can intervene in these processes, and they can use the other electron acceptors if there is no oxygen. So here we are saying this oxidation reaction is releasing electrons which can be taken up by oxygen to produce the water molecules, whereas if you have bacteria that can take up the electron acceptors when there is no oxygen, then what are you going to get? You are obviously going to get anaerobic digester reactions. Examples include nitrate becoming nitrogen gas, N2, sulfate becoming H2S. So ocean, for example, has sulfate. So in the ocean you don't get methane production other than in the sediments and hydrates. Well, hydrates are the storage, but this is why land fills and other anaerobic digestion gives us methane on land, whereas in the ocean you mostly produce sulfides. Also, surprisingly, organic carbon itself forming CO2 and methane. So half reaction there, we can write CH2O plus 4H plus 4E minus. So now we are splitting the carbohydrate, and then another carbohydrate molecule is going to get in the middle and use up the electron as a receptor to produce methane and water, giving us the overall reaction that two H2O molecules are going to give us CO2 plus methane. So basically we are talking about biogenic methane, and at the bottom of the ocean under high temperature and pressure there is also some thermogenic methane production, but most of the world is completely made up of biogenic methane, other than some regions, special regions where lots of thermogenic methane can get produced as well. Hydrogen gas is produced essentially by using hydrogen ions from water as an electron acceptor. So from H2O we get 2H plus, which can receive electrons to become H2. Every time you have these charges, they are desperately looking for electrons, and they become neutral and they are happy. And reacting the hydrogen with CO2 to produce methane goes this way. 4H2 plus CO2 gives us CH4 plus 2H2O. So the overall gist of it remains essentially the same, that organic carbon provides reducing power to produce methane. So you are going from one reduced form of methane, of carbon. Organic carbon, CH2O, is a reduced form of carbon, and methane is one of the strongest reduced form of carbon. So we are just going from organic carbon to methane, which is a good fuel. There are also acetate fermentation reactions. That's a dormant pathway for methane production in freshwater settings. So here, CO2 production by H2 is dominant pathway in marine settings, as we said. And in freshwater systems you have acetate, which is getting fermented. So basically fermentation is a process where some species have evolved to use the chemical energy in the bonds to get their energy, and they end up producing, obviously as a byproduct, carbon dioxide and methane. Okay, so fermentation is obviously used for many reactions by human beings. Putting it all together, methane sources and sinks in teragrams carbon methane per year, or converting it to gigaton carbon per year. You can see the huge conversion factors there. Natural sources include wetlands, termites, which have developed guts with ability to use fermentation to produce methane. Archaea have evolved to use cellulose without oxygen. They actually would die in oxygen to produce methane. Cellulose, there is a huge amount of it. It's the most abundant large molecule, and yet none of the other species have evolved to digest it. We all need enzymes to digest carbohydrates and so on. So these are doing it directly by using anaerobic digestion. Geological sources, total number of sources here is about 230. Artificial sources will include rice farming, ruminants, energy industry, landfills, biomass burning, and total artificial sources, and the total of this plus this in terms of gigaton carbon. And there are sinks. We will look at a tropospheric hydroxyl radical, which is called a detergent of the atmosphere, because an incredibly reactive radical which uses up all kinds of species to wash out the atmosphere. Soils take up some, stratosphere takes up a small amount as well. So tropospheric ozone scrubbing radical reaction is the biggest one that we will look at. So you're accumulating 540 minus 510 per year, so about 30 teragrams of methane per year. Okay, so we will just conclude this by saying that most of the methane produced in sediment comes from organic carbon through a reaction like this. You have the rain of carbohydrates produced by photosynthesis. A tiny fraction of what is produced makes it to the bottom. When it does, in the sediments there are reactions happening, many thermogenic productions, which convert this organic carbon into methane and CO2. Okay, so we'll look at the other the sources in a little bit of more detail in the upcoming podcast. But just make sure you understand the basic reactions, which are fairly straightforward, and hopefully I didn't rush through them. Okay.